Thanks, Marco. Yeah, thanks for having me here. It's been a real pleasure so far and for the opportunity to speak. I'm going to talk about work from nearly a year ago now with Marlena Laverty on neutrino masses in response to everything that happened post DESI's first data release, as well as uh, forthcoming work, just as our thinking about the problem has continued to evolve and as new data has come in. And then at the end, the last 10 slides or so will be on dark forces, which we've already discussed a fair amount, and there are experts not in this room except for Salvatore, but they will be in this room, and pretty much all of them organized the workshop as well. So it's a real pleasure to get a chance to talk about that shortly before the work comes out. Um, so I don't need to tell people here how important neutrinos are to cosmology, and really like the two main predictions of the standard model for their cosmological dynamics, while relativistic, have been striking successes in cosmological data, specifically CMB data, namely the predicted proportion of energy density after they decouple from the plasma, and the fact that they are collisionless after that time, which leaves unique signatures and primary anisotropies. And as is very well known, the uh, third prediction that they eventually become non-relativistic at a you know no later than some maximum temperature, uh, least upper temperature or something, would become non-relativistic, free streaming component of matter, has not yet been seen, and in fact, we largely see what we can interpret as the opposite of their expected effects. So, since though there are actually signatures in the data that have been around for nearly a decade that point to this issue, things really um, really evolved after DESI's first data release, where the nominal minimum mass sum that tells you that they should become neutrinos should have become non-relativistic at fairly early times in the matter-dominated era is almost excluded at the 90 whatever, I don't care, percent level. So the name of the problem is why don't we see the signatures of massive neutrinos that we expect to see based on laboratory measurements of neutrino oscillations? Some people have asked the question, do neutrinos have negative mass? I don't think anyone has really asked that question seriously, but that is the language that we've gotten trapped into using. That said, it is a useful mnemonic, say, for the fact that, as I'll explain, the signatures that we expect are the opposite of the signatures that we observe. And I'll say that I think this is, to my mind, this is the most important problem in this area of cosmology. We can't really make any claims at all about the dark sector if we can't even reproduce known physics. And so I don't think we can really move forward as a field in saying anything beyond lambda CDM without properly understanding how neutrino masses fit into this and fit into our current observations. And so yes, that would be one's dream. Uh, the, oh, the problem is that's a worse fit than no mass at all. And it's a worse fit than negative mass in whatever game you might concoct to. So sure. So the point is that if you okay, like from a phenomenological point of view, this game is useful for diagnosing signatures in the data that don't fit within the models that we have in the priors. If you, so I think I think, starting from this angle is useful as a way to think about new physics that may explain these unexplained features in the data. And, it is a bit odd that they just happen to exactly counter what we expect from standard model physics. But that's what we've got right now. And my point in this box is that to do something with that, you really have to understand, properly what's going wrong, what specific dynamics within our model are generating these anomalous features. Um, and then you can go on to new physics, as I will at the end, uh, to hypothesize explanations. Yeah, so this challenge is an opportunity for sure. So okay, so essentially what I've been working on in the last year and a half is trying to really clearly articulate all of the physical components at different cosmological epochs arising from different regimes of dynamics that feed into the actual measurement of neutrino masses, um, and something that's very useful is the fact that, as I said before, they necessarily become non-relativistic deep in the matter-dominated era, again, within the masses that we expect from experiment. And even if you threw away, even like a very conservative limit where you throw away all of the anomalous, the data that opposes the predictions of massive neutrinos, you still would be in a regime in which they become non-relativistic after a combination. And so this is a useful separation where I can think of the dynamics that generate the CMB at last scattering as in a universe where neutrinos are fully massless, and then more or less the dynamics that occur afterward for all the low redshifts that are relevant to any other observable live in a universe where the neutrinos are fully non-relativistic. This is an extremely useful and very reasonably, very accurate approximation for interpretation. Of course, that also means that we necessarily need multiple distinct observables to ever measure anything, and so that that has its own challenges. But that's the cosmology we've got. Okay, and so the prediction is that at redshifts around 100, the neutrinos become non-relativistic, and at that point they have they comprise a fraction of the total matter density, around 1%, 0.5% at the minimum, scaling with the sum of their masses. So let's go in chronological order. The steps to measuring neutrino masses, the first thing you have to do is calibrate initial conditions, as well as the absolute density of the different constituents, which we can do most cleanly with the cosmic microwave background anisotropies, which, as is very well known, very well appreciated, is more or less a snapshot of the universe at recombination, so redshift 1000. And in the primary CMB, there's remarkable information in all of the different constituents, namely the relative peak heights, measure the ratio of baryon and photon densities in the neighborhood of recombination. More broad scale effects like radiation driving, as it's called, and the early ISW effect. The dynamics of metric potentials on order Hubble timescales give us information about the total matter content at recombination. And so one way to think of this is it tells us how long before recombination the matter era began. And now, and these are dimensionless ratios, which is necessarily what we measure because a map of relative fluctuations in the sky is a dimensionless observable. So you always have to land on some dimensionless measurement. But in lambda CDM and standard cosmology, where we've measured the CMB temperature so precisely that we forget that it's actually a cosmological parameter, and we have, again, a well-reproduced standard model prediction for the relative abundance in neutrinos, that we know what the radiation density is, we know what the photon density is, we have a model for their, their evolution at high redshift, and then we can use that to isolate the present day baryon and CDM densities but really we're measuring these density ratios at early times. Okay, and then there's also the damping tail, which actually doesn't provide unique information on lambda CDM, but it's fairly well reproduced, which is a success of the model, I would say. Okay, and then the second best measured number in cosmology next to the CMB temperature is the angular extent of the sound horizon, as Melissa talked about. So it turns out that in lambda CDM, the size of the sound horizon, again, given the calibration of the CMB temperature and therefore the radiation density, is more or less fixed. You know, for our purposes, we can consider it a number. And so the name of the game then is with whatever your late time cosmological model is, you have to dial parameters to fix the distance to last scattering to get this angle on the sky correct. And usually the most weakly constrained parameter direction remaining in our models is the dark energy density. So a theme will be the implications of physics beyond dynamics beyond lambda CDM, strictly lambda and cold dark matter at late times, and how one has to adapt the dark energy density to fix this constraint in response to those extensions. So specifically, for massive neutrinos, the heavier they are, the denser the universe is at early times in the matter era relative to if they had just remained relativistic and diluted faster. So that shrinks the amount of distance photons travel at those early times. And it turns out that to compensate for that in the very narrow window of scale factor that the dark energy has any effect on how far photons travel, you have to dial the dark energy density, the size of the universe in the dark energy dominated era by quite a bit to compensate. And like the area under this curve, like the way I've plotted this is so that the area under the curve is the distance to last scattering. So this is, you are actually visualizing the proportionality of the effect. So this is the origin of the known degeneracy, geometric degeneracy in the CMB with massive neutrinos, where the Hubble constant is smaller in cosmologies with heavier neutrinos. Any questions? So that's how the CMB calibrates the information that we have at early times. In particular, I'm focusing to start with on information that's relevant for the geometric side of things, so the expansion history part. Of course, we've been talking about suppression of structure all week, and I'll come to that, but I'm also going to kind of count on that being a bit more familiar to most people. Okay, so after we've calibrated, you have to extrapolate this gulf of like 6 or so E-folds between recombination and the late times at which we have any other observable. And this is where our model does most of the heavy lifting and has the most kind of leverage to break things. We need to know how things propagate from last scattering to today. Now, for the expansion history side of things, for geometric probes of the universe, the most important consequence of what I showed here is that I'm changing the balance of matter and dark energy in my otherwise lambda CDM looking cosmology, and that distorts different distances because that changes when you can see it here. It changes when the universe switches from matter to dark energy domination. And therefore, the relative distances as a function of redshift are going to look different as I dial neutrino masses, even without knowing anything about the absolute distances. So I've superimposed here the DESI measurements of the transverse distance. Obviously, that's not all the information that DESI has, but that's the thing I can most easily compare on this plot. And whereas heavier neutrinos necessarily lift this curve upward, you can already see the negative neutrino mass preference, even just at the level of the expansion history, is the fact that all these data points skew low. So I'm going to be showing plots like this quite a bit. It's maybe the only parameter plane in which I show posteriors, uh, and it's a very useful one because it in lambda CDM, so in cosmologies whose dynamics at low redshifts resemble a pure lambda cold dark matter model. Uh, this plane completely parametrizes the acoustic scale measurements that we make. So the BAO measurements and also the acoustic scale information in the CMB are completely parameterized. I've got all the information, even independent of early time physics, because I've chosen to scale the dimensional matter density by the relevant length scale in the problem, which is the sound horizon at the times that baryons decouple. Um, so this doesn't let me get like absolute numbers, but again in models that don't depart significantly from lambda CDM at early times, the sound horizon is more or less a fixed number, and so by scaling it to what that mean number is, you really can kind of just read this axis in as the standard matter density. But of course, in detail, it's not totally correct. Okay, and so in this plane, you can visualize the problem. I have some measurements from the CMB. The black is the calibration, and I'm showing specifically a posterior here with no neutrino masses because I want to isolate the information that the CMB is telling me about early time matter components, namely baryons and CDM, and uh, and so that kind of sets some that calibrates, as a to use my jargon, some minimum expectation of an amount of matter that should be around at late times. And what I would want to do is use something like DESI to then tell me what the matter density is at late times and take the difference and get a positive number. But we get a negative number, as you can see from just comparing the orientation of DESI and the CMB posterior there. Um, I've also, just for fun, shown you what supernova give, and in particular the Cepheid calibrated supernova distance ladder, which is so far out of the realm of plausibility in this plot. It's just a statement of the Hubble tension. Now, if I imagine, if I want to reduce the information that I'm getting out of the CMB to just the bare minimum, which is the acoustic scale, so I'm removing the calibration of the baryon and CDM density, imagining that I have some way to mess with that. Then this white band is the generalization, and that essentially is the BAO information from the CMB. And so is as model model independent as I claimed the DESI BAO posteriors in this plane are. In other words, like there's no point to thinking about parts of this plane that don't live in this white line. Again, in cosmologies that look like lambda CDM at late times. So right, so from this plot, I'll have a better plot pretty soon for specifically isolating that. What I would say is, I mean, yes, like the DESI BAO are relatively consistent with the SDSS BAO. I mean, they moved in the wrong direction for neutrino masses, but all else equal, they're fine. I'll come back to supernova, and yeah, I would say, like, I don't know, you might be tempted to say, oh, well, how, if there really is something wrong, like, wouldn't it be a coincidence that the CMB line just happens still to slice through DESI? And I don't know how to evaluate that, but yeah. So, but the point I'm trying to make is that you really need to like zoom in on the plot. Like I really should just be making the plot live within this band, and you need to ask questions along that band. And yeah, just open a couple slides, I'll have a better depiction. But before that, though, so yeah, exactly. The last step is to infer neutrino masses from this comparison. And as I said, I expect an increase in the abundance of matter. And to do that inference, I need to fix something about late time dynamics, which here is in the form of fixing cosmological constant. Okay, so this is it's the next slide that will be the one that will be most effective. But just to as a first step, what I'm proposing is that you have a top axis here, which is a linear transformation of the bottom axis that uses the uh, standard models calibration of the number density of neutrinos when they decouple, the measurement of the matter density from BAO data, and it's specifically BAO data combined with the CMB's BAO information, so what I would refer to as broadly the acoustic scale, wherever it comes from. And then factoring in the calibration of the density in, well, the drag horizon, as I mentioned before, and the density and components, matter components that were around at early times, which is only on this plot in the form of the mean, the posterior mean, which I've shown as a vertical line. So let me just skip right to the more useful representation, which is now I'm combining my CMB BAO information, the white bands, with the direct measurements from galaxies to to do that game of specifically measuring things along the CMB's geometric degeneracy. And the problem statement is that the black, the amount of matter that we extrapolate from early times as we measure in the CMB is shifted to the right of the matter density that we measure from the acoustic scale in all of its forms that tells us directly the density in matter at late times. So this is I mean, in minute detail, like the degree of the tension, it looks a little bit different for neutrino masses because of, because this is just, an approximation where I'm assuming that the neutrinos are non-relativistic at all times and, details like this. But this is my clearest representation of the problem at the expansion history level. And I mean, it's not more than say 2 sigma, but the things to bear in mind are, one, my standard model expectation is even further to the right than what I'm showing in black, because that's just baryons and CDM. So 0 neutrino mass is not enough. And 2, when we do the physical thing and try to constrain neutrinos that have a meaningful mass, that is to say a non-negative mass, the upper limits that you get are exponentially sensitive to these shifts because you're truncating a posterior in its tail. And so tail measures are in a Gaussian are exponential. And so, even like a fraction of a sigma shift is going to give you an exponential effect in your tail measures. Indeed. Yeah. Yeah, okay. So the gray line. So yeah, I probably should have put it on this plot, but yeah, so like here, so I mean, yeah, you shift the black by like something like this amount. Say that again. Yeah, but then you add in quadrature. Well, yeah, and also these are not independent measurements because both have the CMB's theta S in it. Although that's not really relevant for the CMB's measurement. So yeah, but then add in quadrature the errors, that's how you get around 2 sigma. Any other questions? Okay, cool. For the sake of time, I'll just very quickly say that, well, I already said supernova measured distance is 2, and there's when viewed within lambda CDM, there's a ever-growing tension between supernova and BAO just in what they tell us about relative distances. So to kind of show how this has evolved since 2018, Um, you know, where we had like the earlier iteration of the Pantheon sample, and then some measurements from EBOS, to 2022 when we had the all of the EBOS data, all SDSS and Pantheon Plus. You can see things shifted a bit, and that's in 2024 got more extreme with DESI DR1 and DES supernova, which both continued the trend in opposite directions, and earlier this year, DESI just made things even worse. So what this means for neutrino masses is, in fact, that according to our priors, the supernova data is more likely to be correct. And by priors, I mean on neutrino masses, not on any other consideration. And you can translate this into what turns out to be a 3 sigma measurement of non-zero neutrino masses. So this is doing I mean, all of these plots here are like, toy in the sense that it's not really neutrino mass. It's just different matter densities at different in different observables, just for the sake of illustration. But this is actually a full analysis of the data where all I've done is marginalize over the amplitude of CMB lensing so that I can, in some sense, isolate the information from the expansion history. This is not a perfect decoupling. There is an interaction between these two measurements, which is important, but for the sake of what I'm showing here, just let's forget that. Yeah. So yeah. Oh, yeah. The numbers are the 95%, 95 percentile, and then the white lines are median and plus or minus 1 sigma. No, they all have Planck. Yeah, yeah, yeah. Without lensing, and moreover, I'm marginalizing over a lensing amplitude parameter so that, yes, just that it's the simplest way that I can isolate that information. One could imagine something more complicated, but I don't really care to work harder, which will be what I talk about next. Yeah. Indeed, because I'm showing you half the story. Yeah. Okay. Any more questions? Okay, so now let's return to the steps. Now I'm going to talk about lensing, growth of structure. As everyone knows, neutrinos are fast. Even when they're non-relativistic, they are too fast to clump with the dark matter, and that has the net effect to slow the rate at which the dark matter itself can clump. And so that means that there's a monotonic decrease in lensing power, or any tracer of the underlying matter distribution as I increase neutrino masses. And as you can see, maybe not quite so clearly as in the case of the DESI data for the expansion history, there certainly is, in the existing lensing measurements that we have, this is reconstruction measurements, a trend to go higher than the baseline zero neutrino mass prediction rather than lower, which is what we would want to see. And so to do the steps of like what what I calibrate from the CMB, so information at early times, how I extrapolate dynamics to late times, and then from what I measure at late times, then infer a neutrino mass. I'd want to identify a decrease in accumulated structure growth. Heuristically, what that looks like is taking the high L temperature and polarization anisotropies as a measurement of the initial conditions, so AS, the amplitude of primordial spectrum, including the suppression from reionization, identify from the unique signature of reionization in the CMB how large that suppression from reionization is, so that I can then identify what the initial conditions were, what AS is, and then use my model, so extrapolate from those early times to late times, how much structure should have grown, what what lensing power I should measure, and then hopefully identify decrements that I can attribute to neutrino masses. So when all is said and done, so I for our paper last October, I concocted a way of doing structure only, so trying to remove the geometric information. That didn't make a results plot here because it's actually a much weaker measurement, which, for which the moral is that you really need both of these pieces of information to understand neutrino mass measurements. But so what I'd say is most interesting to look at is just the addition of the structure information. So the top panel is all of the CMB data that I had available to me a year ago, and then I've updated it with the latest DESI data, as well as as well as the older iterations. And so even with the lensing excess, the CMB lensing excess that disfavors neutrinos from suppressing structure, the DES measurement of the relative distances that tells me the matter fraction that combined with the CMB then identifies a late time matter density. Even that's still strong enough to give me a marginal preference for non-zero neutrino masses, which I will let you, make of what you will. And just to say in a bit more detail, so the I think before a year ago, the importance of the expansion history was not fully appreciated, and also some ways in which it interacts with the enhancement of, the lensing based measurement, specifically, dialing down the dark energy density. So dark energy era starts later. Dark energy also suppresses structure, and so the at fixed dark energy density, the neutrinos may suppress structure by so much, but that gets partially compensated when you fix theta s, because that requires you to dial down the dark energy density. And I would contend that it does not make any sense to, there's no unless you take shoes more seriously in lambda CDM than theta s, then it does not make sense to fix any parameter other than theta s. If you want to fix h, then solve the Hubble tension, and then I'll listen. But yeah, okay. So but when it comes to the lensing excess, I think I don't really know, but people seem to have mixed opinions on what its status is, and in reading through literature, the way that the CMB papers have discussed the issue in their own data, I don't think people have clearly articulated the question that is most relevant to physics. Namely, the thing to remember when interpreting a lens, and specifically when one survey may say that they see no evidence of a lensing anomaly, is that a lens is a relative thing. So I have some cosmological parameters that describe the actual physics, and then whatever those parameters are, the a lens is just an enhancement on top of that. So it's not actually telling me anything about the absolute amplitude of structure, but rather the relative amplitude relative to what I predict from the actual physics. And so to actually reason about what the observables are telling us, you have to look at the observable, and essentially understand how the calibration of the other cosmological parameters from CMB data are or are not informed by trying to fit some amplitude of lensing. So what this plot's showing is the residuals of the CMB lensing spectrum. This is this is like the thing that we try to reconstruct from higher point statistics, but it also is a useful proxy for the degree to which the primary anisotropies are lensed. And on the left panel, I'm showing you the purest calibration from early time dynamics that has no information about lensing that I can come up with without working really hard, which is to just truncate Planck at sufficiently low L, meaning 600 to 1,000 or so that all of the information on the CDM density in particular, but all the cosmological parameters is mostly coming from early time physics rather than late time physics. In other words, essentially the unlensed part of the CMB. And I'm coloring these curves by the CDM density. which becomes which is the critical parameter to interpret the comparison between different surveys. Now, the middle panel is showing the same quantity, but as calibrated by just ACT and SPT's high resolution measurements, whose information on cosmological, on specifically the CDM density, is exclusively coming from lensing physics. I mean, exclusively, almost entirely coming from the impact of lensing on the primary anisotropies. And I also include tau so that I have a common baseline, calibration of that. And you can see that the observable, the degree of lensing, is higher than what the low LCMB wants. I mean, it's not, quantify it how you will, but you can just see that the predictions, like half the posterior here, the negative half of the residuals, or rather I guess I forgot to subtract one here, are excluded, are not preferred by ACT and SPTs. And at the same time, that higher degree of lensing is achieved through a higher CDM density, which pushes the equality scale to smaller scales, and therefore the turnover in the matter power spectrum to smaller scales, so that the power that does lens the CMB at late times is higher. Yeah, those are the quantiles, median plus or minus one. You mean the white, black and white? Yeah, it's the median and plus or minus one quantiles of the sample, the posterior sample I'm showing here. Okay, and then if I take all of this data, but then give it the freedom of a lens, I see consistent lensing amplitudes in the actual observable, but lower CDM densities. And so the takeaway here is that when you only look at the high LCMB, you only have information from lensing. The model is free to adjust parameters like the CDM density in order to fit the lensing signal. And therefore, you're going to get a lens of 1 because you're not adding anything that the model needs. But when you fold in the low LCMB data, that, low meaning, below 600 or 1,000 or whatever, that's when you need that freedom to concordantly fit the information on the CDM density from low and high, from unlensed and lensed information. For the sake of time, I won't explain this in detail, but the preference for excess lensing is concordant between the high LCMB, the lensing of the primary temperature and polarization anisotropies, and the reconstruction from higher point statistics. This is again nuance in what question are you asking. If you allow your model to be calibrated to the lensing that temperature and polarization want, then the 4-point reconstruction is happy, gives you an A lens near 1, because you're already calibrating to data that want a higher lensing amplitude. If you ask the question, is there a preference for a common increase of lensing between the two observables, then the answer is yes. We can talk about that in more detail, but I want to get to long-range forces. Tau has been of interest lately. Marlene and I also checked this a year ago, and it essentially plays the same role as a lens. So the same geometry only figures I showed you before are essentially equivalent to just removing the information on tau we get from very large scale polarization. Yeah, okay, I'll just move on now to dark forces. So the summary is that I've said it a bunch of times: calibrate, extrapolate, inference. I can modify any of these ingredients and perhaps rescue the measurement of neutrino masses from data. And the one I will talk about is dark forces. And since Diego wasn't in the room, I'll just say, Diego and Salvatore and Emanuele and et cetera, have really provided I think the most useful treatment of these models that I became very interested in because what they told us about specifically the importance of the background. I became interested in relation to these neutrino mass problems. So specifically, so I've written down the action of a scalar field with coupling to the mass of a gas of particles and the kinetic theory description, and that coupling is actually the way in kinetic theory that you use a scalar to mediate long range forces, and whatever your description is, that gives you a effective potential for the scalar that's going to govern its dynamics unless you invoke a bare potential that um, uh, to do otherwise. And the lower energy configuration is that with lower mass. And so you might imagine that this model gives you a way to solve this matter density deficit by changing the way we extrapolate the density in early time components, baryons and CDM, or not CDM in this case, just dark matter, from recombination to the present. Moreover, the dynamics of perturbations show that there's an additional force that can increase the rate of clustering of dark matter. And so you might imagine that it also solves the lensing excess. Now, Diego and company already appreciated that the enhancement of density perturbations that does happen in this model, and that you would expect even from analytics, is not reflected in the CMB lensing observables, which reflects some competition between background effects and perturbation effects. And really, I became interested in these models because I wanted to understand why that was in more detail. Specifically, with the idea in mind of is there a way to modify that result? Is that telling me something deep about physics more generally? So in that pursuit, uh, we, and I should say this is with Cyril and Olivier and Marco Costa, Diego's collaborators, who will be here next week. You can write down an effective second order differential equation, the usual one that we write down for the growth of density perturbations, augmented with two features that come from inserting the subhorizon limit for the mediator, the scalar, which gives you a friction term that accompanies Hubble, and then an enhancement of clustering. So effects that resemble GR show up in the same way, and without actually really assuming anything about the model other than that these terms don't vary fast compared to the Hubble time. You can write down a analytic solution for the growth index. So if I were to take an ansatz that the density perturbations grow like a to the power, this is that power. Yeah, Mustafa? Yeah, I'll maybe I should have permuted my slides, but the field remains frozen. I'm only going to talk about massless fields. The field remains frozen until the dark matter density becomes important enough relative to the total density, so around equality, that this potential competes with Hubble friction and drives its dynamics. It is dynamical, although I have not assumed that here. Like that any dynamics would show up here in some form, so long as the approximations I made in this equation are suitable. And it would also show up here in that it makes a contribution to the expansion history. I think, so I don't want to get too technical, but since we've got the experts in the audience, this is like a slightly different way of understanding how the dynamics enter Hubble. Which I can show you in more detail. It's superficial. And then in addition, the fact that the mediator does not cluster. It acts like neutrinos, in fact. And so it decreases the growth of structure by the same amount, depending on the fraction of the matter that it contributes. And in fact, you can see from this expression that plugging in F phi for the non-clustering fraction here, which could also include neutrinos if you like, I have a equation of state minus 1. And so without a potential, these effects actually cancel. The equation of state is, so it's the ratio of the pressure and the kinetic energy, which is always 1 for unless I have a potential. Because the pressure and the energy. Oh, yeah. Yes. Oh, yes. Sorry. Yeah. Yeah, sorry. Yeah. But of course, to spoil a bit, as you've already shown, bare masses only make this problem worse. They'll only suppress structure. Yeah. So, but yeah, I'm making statements from here on out for massless mediators. I don't often read titles either. It's fine. Okay, so what this means is that in the regime that I'm going to talk about, there's really just a competition between the modification of the friction, so the analog of Hubble for the long range force, and the enhancement of clustering. So as Diego showed us, we have some analytic solutions that work extremely well in these theories, and what you should have in mind is that the mediator has some logarithmic evolution after equality, and that what that leads to that's important for this equation is a extra friction that is of order beta, which is the relative strength to gravity of this force, times the fraction of dark matter in that experiences that force, and then the mediator fraction, which I already said cancels out here, but it's also fully specified by the relative force strength beta and the dark matter fraction. And I'll keep inserting, even though we already know it's going to cancel, I'll keep inserting them just so you can see. Okay, that's not what I meant it to be, but that's okay. So if we plug in these numbers, so this is like a relatively pedantic correction, but I think instead of 6/5, it's really just 1 beta f chi squared is the modification to the growth index, and that originates from accounting for the fact that this is a non-clustering component of matter. And to check, we just measured this number from class, so solving the full Einstein-Boltzmann system with this model, and then numerically calculating the growth index. The y-axis here is meant to be a measurement of these coefficients, the numbers. So you can squint at the definition of the y label if you like, but essentially this confirms that the growth index is modified by 1 beta f chi squared in the full model, and I played this game where I like shut off the modifications to the background evolution and shut off the modifications to the perturbations evolution. And I call this perturbation and background only. It's not. There are background effects in the perturbation equation that from like the friction and whatnot that are, so it's not like perfectly compartmentalized in that way. But you still what you should see is that you still get the 3/5 that is expected if you only enhance clustering. And then the blue here is really just if the perturbations evolve as if they're CDM, but the mass is dropping with 1 times this combination of parameters beta f chi squared. Okay, so this is, I mean, okay. I've so far I've told you nothing new other than that 6/5 is 1, whatever. That decrement of 1/5 actually turns out to be pretty important in the next result, which is that the density contrast is not the observable. The lensing potential is the observable, and lensing potentials are sourced by the total density perturbation, not the relative density perturbation. So I have to fold in the fact that the mass is dropping, the absolute density is dropping at the same time that relative perturbations are growing faster. And so if I do that, and then I plug in the numbers, I actually get that the growth rate of observable structure, so lensing, or metric potentials, uh, is completely unmodified in the matter era. There's an exact cancellation between the background modifications and the perturbation modifications. And again, I've played the same game of measuring it from full solutions, and indeed that's what you get. So this is like kind of like super interesting. It means that there's no intrinsic ISW effect from the modification to the growth of dark matter structure. And it kind of, I think, makes even stronger Diego's case that the background is the most important feature of these models. So this is this is the answer to the question that we arrived at, and trying to understand in more detail, what it is about these models that makes them insufficient for solving the lensing excess. I've got like 2 minutes, so I can quickly say, this is a story that Diego and Salvatore have also already told. That with DESI, what looks like a matter density deficit in lambda CDM gives you some preference for the mass dropping between recombination and late times. And the second real point that we have, I think, to contribute is the fact that, again, returning to this idea that the global expansion history quantity that I should always have fixed, this theta S, in order to accommodate this decreased dark matter density at late times, I have to greatly increase the dark energy density. And as I briefly mentioned with massive neutrinos, increasing the dark energy density makes it suppress structure earlier. And it turns out that the response to the dark energy density at fixed theta S to the long range force is severe enough, steep enough that it actually makes quite a difference. So the solid curves are showing you the drop off in the sensitivity coefficient in a lambda CDM, well, a lambda long range force dark matter universe, compared to the dashed curves, which are a pure matter universe with no dark energy. And the punchline is that long range forces actually suppress structure rather than enhance them. I mean, this is a bit of an overgeneralization because it's specific to the case of a massless mediator, but as I mentioned before, Diego and Salvatore already told us that adding a mass for the mediator doesn't help. For the sake of time, I won't explain that here. This is the same style of plot that I showed before, and it's just showing you that the parameter that's really governing the amplitude of lensing is the CDM density, and that story does not really change in the presence of the long range force. And if I want to specifically try to pinpoint the effect of stronger long range forces, that's what this last panel is showing. Curves are colored by the long range force strength, and you can see, in the mix there are darker curves with I mean, certainly some tilt, but in the territory where I've got these residuals that are skewing this way in the lensing reconstruction data, the model is giving me the exact opposite. So unfortunately, not a viable solution to the lensing excess. An amusing corollary is that that long-range forces can suppress structure and therefore solve the S8 tension. Of course, you wouldn't really know this if you just looked at sigma 8, but again, the S8 tension is coming from weak lensing observables, cosmic shear. So you have to ask questions about the observable, and indeed you can see a very strongly negative sensitivity of galaxy lensing spectra at low redshift to the long-range force. Okay, so I'll conclude there. There are two problems that look like negative neutrino mass, matter density deficit between early and late times, and a lensing excess where I want structure to grow more than I can easily predict. And I think this, I'm trying to arrange this as a framework for understanding the data, so the observables and their relationship to the physics, as a guide for thinking about BSM that might better fit our data, and hopefully future surveys will provide unique insight to help us differentiate from a bunch of solutions that have indicated up on this plot. Thanks.
So the question that I have now, so related to this, follow up question. So what should I take out of this discussion? So omega m lower is a success, and the lens is a bit different one. Right? So in the end, if I combine the two data sets, they tend to, I mean, for instance, within this model, they tend to go one against each other.
Yeah.
So it seems that the model would be compatible with both should somehow have the feature of giving the it's an enhanced dark matter clustering, but mostly at lensing scale. Right? So the problem with long range forces is that they are enhancing clustering at n scale. So indeed, from the power spectrum, you see it very clearly. So it's just an overall rescaling of the power spectrum. That's the problem why they are very degenerate. For instance, the linear balance of that.
So no, so yeah, the point is that lensing isn't. Yeah, the point is that our unbiased tracer lensing also factors in. You have to multiply by the density, the background density, and so the model is not a successful way to enhance that quantity. So this, in other words, like the structure that we observe that is telling us that it wants to be higher is sensitive to the total density perturbation rather than the relative density perturbation, and long range forces mediated by a massless scalar do not actually enhance that quantity. They enhance, yeah, yeah.
That the weighting of every say distance is flat. So if I have now a theory, so you see, like when you're doing the integral, every length scale is just rescaled by the same amount. If this is if now I have a theory that weights differently, it doesn't cancel. That's my gut feel.
Yeah. So specifically, so I think, yeah, no, I think you're right. Exactly what you're saying is why these darker curves are slanted rather than flat. Now, like that doesn't really like the point. Yeah, all I'm saying is that the actual growth that happens over time is not increased. Yeah. So yeah, so like, but then okay, if you want to get more creative and try to rearrange these things, I mean, I've been thinking about this from kind of the perspective of if I take, because that's an expansion history effect, okay, and it's mostly a low redshift expansion history effect, and so I have direct measurements of distances to calibrate that possibility, and from what I've seen, there's not a lot of wiggle room to play that game of distorting the mapping between scales and observable lensing multipoles without that actually satisfies the DESI data, let's say. So that, yeah, it's an interesting question and something one should bear in mind when thinking about the relationship between physics and observables. I have no compelling model to offer you that would do that. Yeah, and I guess to return kind of to your original question, I would say that the data seems to be happy with density decreasing and density decreasing compared to CDM and structure increasing compared to CDM, and the neutrinos go the exact opposite direction. Long range forces go orthogonal. I've not found anything that I actually I have some upcoming work that after this that will or I'm trying to find something to enhance structure, other than like things other than long range forces, and I've not really been successful in finding things. So yeah. That's the opposite of what you want. That's what neutrinos do. Yes. You want to move to the left on this plot. Yeah, yeah, yeah. Yeah. Negative neutrino mass is a useful mnemonic. I have to grant. Yeah.
One very rough way of saying.
Yeah, yeah. So yeah, I put that on here because Lloyd Knox and Gabe Lynch looked at this, and it does move you in the direction that I indicate as far as geometry expansion history goes, but it suppresses structure for two reasons. So one, again, bearing in mind that lensing cares about delta rho and not delta, you're decreasing rho, so however much you decrement the however whatever fraction of dark matter decays decreases lensing by that fraction, and then the decay products are relativistic, unless I don't know, they're relativistic, and that also suppresses structure because you've got a free streaming subcomponent. So it goes in fact the same direction as the long range force.